have to take a functionalized aromatics to introduce the as a source of the surrogate of the aryl rings, and it has a dependence on the particular directing group. So we realize that here, as a medicinal chemist, we can contribute to new knowledge of chemistry also, particularly if we can address those advantages, like can we replace that butyl hydroperoxide, which is used at least 10 equivalent as an oxidant. Generally, naturally, it is going to generate a lot of byproducts also, which has to be purified at the late stage. So can we use oxygen as a oxidant? Then can we make it a strategy which will be independent of the directing group? It can be more than one directing group. Most importantly, can we take an aryl methane, so the hydrocarbons which are very easily available, so that we do not have to take a functional molecule? So all those things we took into the picture, and we realized that the palladium catalyzed reaction under the organocatalytic influence of NHPI, which can activate the oxygen molecule, we could get the arylation in a very diverse way. So we have prepared the various kinds of arylated benzothazole. Then to have a proof of concept, the reaction really proceeds to the CH activation. We did some kinetic studies, which is popularly used by the organic chemists. We determined the KH KD study, and we could find out through the NMR study a appreciable amount of the KH and KD effect, the kinetic isotope effect, which tells that this is going to be a CH activation study. So to have being in the NMR, what we have to do, we have to isolate each and every reaction and isolate the compound, and then do the KD study. We thought that can we add now a sustainable analytical chemistry over here, that we need not to isolate this compound and do the KD study. By this time, we have developed enough expertise in using mass spectrometry, and we thought that can we do it by mass spectrometry, so that it will give a real-time analysis, and we need not to isolate the individual compound. And in case of mass spectrometry also, we did get appreciable amount of the KH-KD ratio. So those two experimental evidence tells that the reaction proceeds in fact by the CH activation strategy. So then we thought that what is the way, and this has been taken that how exactly the other CH activation takes place. We tried to identify or isolate the intermediate organometallic compounds, but it was very difficult to isolate and purify them. But we were satisfied by taking the literature report. We tried to understand that how exactly the benzoyl group is being incorporated. So we propose that this is the way the lower reactions came, that in presence of NHPI and oxygen is activated. So we get the benzyl radical, which undergoes peroxide radical, and ultimately it reacts, undergoes elimination of hydroxyl radical, and we get the benzoyl radical. This benzoyl radical undergoes oxidation addition to the palladium 2 complex 5 and give it to the palladium 4 complex, and then after reductive elimination we get the compound. So this reaction has to be dependent on oxygen if the reaction mechanism has to be valid, and does it proceeds via the radical intermediate, that has to be demonstrated. So we did find out that dependency of the oxygen by carrying out the reaction under nitrogen atmosphere, the first equation, the practically no product formation took place, and also the reaction is arrested when the reaction is performed in presence of stoichiometric and amount of tempo, which is known for trapping the radical intermediate during the progress of a reaction. So further, we tried to prove that distinct involvement of the benzoyl radical, because if benzoyl radical involvement takes place, so there has to be initiation or accumulation of the aldehyde. In fact, through the NMR study, we could identify the presence of the aldehyde proton over here, so it is not exchangeable with DTO. So if aldehyde is being produced, so we can have a more direct proof. Can we trap the aldehyde by treating with a suitable trapping agent? And benzothazole is a very good trapping agent for aldehyde, because they are going to convert to the benzothazole. So we can take either toluene as a precursor of the benzoyl, or dibenzyl ether also can be precursor. And we did find out that if we perform the reaction in the presence of the 2-aminothiophonol, we could identify the corresponding benzothazole. So all those things actually proved our mechanistic proposal, that how exactly toluene is being converted to the benzoyl radical and being used as a surrogate of the benzoyl. But then we realized that if we can generate a benzothazole is our starting material or actual scaffold, and we are using earlier an aldehyde and condensing with benzothazole, but can it be that now a aryl methanes can be used as a starting material to make our dessert starting material? So in fact, we find out that if the reaction can be trapped with various kinds of substitute 2-amino benzothazole, then we get the corresponding benzothazole, 2-aminothiophonol. So now what we did, we have our desired molecule, target molecule, we should have a catechol moiety over here. So we have the benzothazole having the catechol moiety various kinds of toluene derivatives, and we do need to functionalize this thing to a aryl moiety. Then we have to introduce the catechol moiety in the other part, benzoyl part. So here our methodology from toluene, somehow the yield was not much good. So we have adapted the classical way by taking the tricibutyl hydrogen peroxide as the oxidant and take the corresponding aldehyde. So we had all the various substitution pattern, whatever we required to further optimize the biological activities. So what we did, we had our lead structure, which has contributed by Dr. Rudrawar in my laboratory when he was there. Now, later on, maybe after so many years, we could find out. So now these molecules have been evaluated and they are showing much better enzyme inhibitory activity. Now we are in the process to see the selectivity B versus D, and we are looking for a suitable animal model, because it looks like that we tried once in our pharmacology department, but the student gets infected, so I'm trying to outsource this one. So what I tried to present over here, that we have adapted the new development of the chemistry. In some cases, we have developed the chemistry also and made it a practice in the discovery medicinal chemistry for optimization of our initial lead. We now tell you a few examples of how our aqueous chemistry can be used to get the starting material to make our newly designed anti-TB scaffold. So we realize that the benzothazole has a potential to become a versatile scaffold, and particularly anti-TB. Tuberculosis had been the thrust area of the institute where I served for my entire career, Naipar Mohali. So we found out that these are the two compounds which are showing a very good activities, but not as good as is desired to be. So we realize that activity will be practically that if you have a strong electron withdrawing group attached to the benzothazole framework, like nitro group over here, but the nitro group are potential toxicophore and they generate a lot of toxic metabolite. So we wanted to have a replacement of the nitro, and we designed this one because in all the cases, again, particularly the best active molecule, C2 position is being replaced by a amide group. So what I did to take advantage of the electron withdrawing property of the nitro, at the same time to retain the amide moiety, we took a C2 reverse amide, which does not contain a nitro group, and we thought that this might be a better scaffold. So we prepared about then our synthetics work began. So this is the starting material. We prepare it by taking ethyl glycolate and taking the aqueous chemistry by condensing the corresponding chlorphenol. We make the corresponding esters and then subject it to catalyzed transamination reaction, and we have prepared the target compounds, and I think about 41 compounds were synthesized and subjected to anti-TB activity, and we found out maybe total 17 active compounds are there, but out of which maybe we can consider 1 or 3 compound to be worth mentioning activity. So we realized that our number of active compounds is very less number. Probably they may not survive in the subsequent pathway when you try to further develop the molecule. So we need about a half a dozen of the backup molecule of the similar structure. So what to do? So we thought that is there a possibility to further modify the molecules. So this is our best active molecule from our previous support, and we wanted to attach some other bioactive feature which are present particularly in the anti-TB molecules, and we found out that this piperazine moiety is there. I mean, in linazolid also it is present over there. We thought that one way we cannot introduce all the various structural scaffold, but this pyrazine moiety can be very easily thought to be introduced because of the amide bond formation reaction. So we did it, and we got this is again the first step is actually our S-DOS mediated condensation reaction, and then next is that transamination reaction. All those chemistries also we have not separately projected, and those are also is a new way to make the corresponding transaminated product. And we did find out a little bit larger number of molecule having active. So what was one compound and in less than 0.78 and about 3 compound less than 1.56, we got 4 and 6 compound. Particularly we want 0.78 or less than that. So the number increased, but still it is not as moderate as we are demanding. So now what we started initially from the left structure and having 2.3 micromolar. It gives a better flexibility but not much improvement. But fine, we have a larger number of molecules to take it further, but still this is not sufficient. So now what we have to do, now to have a better varieties, we found out that we have a restriction in the pyrazine moiety because we do not have much flexibility over there. So we thought that can we have in general aryl moiety, and particularly if we have an aryl moiety, then NH might be having a much better hydrogen bond donor. So in this regard, we have designed this improved scaffold. And the only thing is that the transamination reaction, we have to adapt a different chemistry. First chemistry, again, our water mediated chemistry. Second chemistry, also lithium hydroxide. We have discovered long back, we have also used lithium hydroxide as a catalyst for different purposes, but this is a hydrolysis to prepare the carboxylic acid. And then we have subjected to classical coupling reaction, CDI mediated. But now we have a different way also. That chemistry at this time we cannot discuss over here. So we have a better way to do the peptide coupling reaction or amide coupling reactions. So with this known CDI chemistry, we have prepared about 77 different types of compounds, and some of the compounds, 72 compounds were subjected, and we did get about 9 compounds, and about 6 or 7 of these compounds have shown very good activity in the resistance model also. So we are now working with the collaboration with Life Science Department of Bombay IT for target identification and taking it further. In the process chemistry, I'll give 2 examples in which our water-assisted reaction, which Santosh has initiated in my laboratory, we have carried forward further and developed a completely all-water chemistries. And in this regard, this molecule is not much complex because there is only one stereo center, but it has been a very new way to treat the chronic angina pectoris, and it has been approved by US FDA by 2006. So but what actually attracted regarding this molecule, but when we started taking interest in this molecule, when we started doing the literature search, we found out many patents are coming. And most of them are US patent, some of them are filed by our Indian companies also. And when we have studied this patent, we found out the patent only talks about how to reduce the impurity in the final product. None of them talks about any new way to make the molecule. So then we realized that if you can get an US patent just to think about a crystallization procedure or how to minimize the impurity of the same processes, so if we can take the origin of the problem, and that is going to be much more creditable. So what we did, we analyzed the structure of the molecule and how all the patent literature and chemistry, other published literature are making this molecule, as has been segregated in the different part. So these are the different components of the molecules, and we realized that how these components are incorporated in the final product, and that sequence actually makes a big deal. So if you can rearrange their introduction in such a way, that particular reaction which happens to be inherently tendency to get a side product, then we can minimize the final impurity in the final product. So we have completely re-engineered the process, and this is the total scheme. And each and every process, we are only water has been used, except maybe one case where we have to take a probably ethyl alcohol as a solvent. Let me check that. Yeah, last one. So what we did, so it is a much overall yield has been increased from 23% to 77%. So the first is basically to make the amidation reaction using water, and then this one step we can do this reaction, and both RS as well as RMS compound were separately prepared, and they are more than 80% yield, and enhancer selectivity is very good. There is no decimation. Most importantly, overall yield has been increased by 23% from 23% to 77%. So this happens to be the monobox protected pyrazine happens to be one of the starting material. But then again, we thought that is it possible that without taking a protected, and it requires a deprotection at certain stage. So can you take a protecting group free synthesis? And we found out that yes, this manipulation can be done very easily in carrying out the reaction in water in the presence of tetrabutyl ammonium iodide, so that if you take this chloride, it will be only reacting with one NH group. It does not give the side, and those are the side product in the reported procedure or obtained. So we got here overall yield is reduced to 69%, but the reaction works very well in two steps. The second molecule we have taken lubelazole. Lubelazole has been approved by US FDA as under the trade name Riluzole. It is because of its various although it has been approved for the treatment of acute ischemic stroke. But what was found out later on, that it works with a versatile drug target, and perhaps it might be a molecule of the future for the repurposing against various other diseases. So this might be the right molecule to do the process chemistry. So here also we have segregated the installation of the various components of the molecule, and all the cases we found out that reaction can be promoted by the water. When we claim a reaction is promoted by water, we parallelly try the same reaction in all the classical organic solvent. If the other organic solvent there is a distinct disadvantage, then only we can claim. Otherwise, we do not claim any water assisted synthesis. So all the reactions, they do not work appreciably in any other solvent. Actually, it does not work at all, most of them. So this is the way we have found out that we have introduced. It is a completely different route from taking from epichlorohydrin. It might be either RS, S or R, so that ultimately we can get all the three product racemic as well as R and S in the 3-step. And later on we can find out that it can be in one pot reactions also. So we have talked about aqueous media, and in the meantime, in the catalysis, nanocatalysis also has been considered to be a one way to address the sustainability. We thought that is it possible to club the advantage of nanocatalysis in aqueous media so that we extract the double benefit of the green chemistry, and we had a problem. As a matter of fact, you are working in the medicinal chemistry, you do not have got the problem to devise new chemistry, only mindset, whether you are going to take the problem or not. We found out this scaffold A is a versatile scaffold. So most popular drug molecules are the beta blockers, but a lot of other kinds of therapeutic agents also, their essential pharmacophoric feature is the scaffold A. And that can be obtained by organic reactions, which is nothing but epoxide opening reaction by the phenol. In my laboratory in the early stage, we have done a lot of methodology or a lot of reactions in which epoxide opening reaction by amine. Santosh says this is a significant amount of the work is based on that, and maybe some other students also. But amines are a very good nucleophile, phenols are a very poor nucleophile. So that's why there are not much methods. So the methods which are available at the time when we started to take up this thing are a very costly reagent, and they are either cobalt porphyrin, or most effective reagent is actually a rare earth metal based reagent. So we thought that is it possible we can take advantage of the polarizing ability of the nanometal, particularly it was known gold can polarize the lone pair of electron, the sulfur. So we thought that it is a oxygen is a hard center, so we have to take a harder nanometal. So we thought that can we take a palladium nanometal and which can polarize the oxygen lone pair of electron and then see whether it can do that reaction. And we found out this recipe, entry number 11. If we take palladium chloride and carry out the reaction in the presence of 0.25 equivalent of potassium carbonate as a base and 0.25 equivalent of tetrabutyl ammonium bromide, which acts as a stabilizer of the nanoparticle, we have found out that the reaction produces a palladium nanoparticles. We have characterized all the details, so the reaction works. This reaction doesn't work in presence of potassium carbonate, whether you're taking stoichiometric amount or not. Potassium carbonate actually prepare a nanoparticle from the palladium chloride, so it is not a merely base catalyzed reaction. Most importantly, when the same recipe was used in an organic solvent, so none of the organic solvent the reaction works. The reaction works only in water. Water not only provide to make the nanoparticle, but water also has a distinct role to play, and we try to accommodate the role of water here through the transition state 1. So here is a case where the palladium nanoparticle is activating the epoxide, and here is the case where water is activating the phenol also, and at the same time epoxide. So dual activation takes place, and the reaction works very well. Knowing the importance of the work, so whenever we find out that any chemistry we develop has a potential importance in the application of the process chemistry, we try to patent them. So this is the motto of NIPER also. What we found out here, although we have not projected in this paper, by this time a new interaction has been added called cation pi interaction, and which might be another parameter or descriptor in drug design also. Here is a case which we have not projected much. Here is an example of anion pi interaction. So what happens when palladium gets the electron density, it becomes actually anionic complex, 8 complex, and that is the reason this interaction is very important. And we found out because of this reason, that if you take para-nitrophenol, the reaction is much faster than simple phenol, although para-nitrophenol is a less nucleophile. So it is not merely dependent on the nucleophilicity. Para-nitro group, it makes it much more electron receiving reagent from the 8 complex. Although in this paper we have not projected it, in the future we'll see that whether you can make it a distinct claim or not. This is the first example where anion-pi interaction is very important for metal and aromatic interaction. So now I take you to the last stage of my discussion where we can use. So what I try to tell you over here, that all the chemistry which is done in the classical chemistry school or even other school also, their objective is not merely to develop the chemistry. Inherently objective is that chemistry is going to be useful, and only useful of organic reaction development is the making the drug molecules, either existing molecules or you can make in a better way. So, and that has been the concern. So we wanted to see that whether nanocatalysis and in general CX bond activation, I have shown CH bond activation, it might be CBr, CO bond activation also, which has been projected in a big way in the last 10 or 20 years. So we thought, can we make into the practice of those advantage of the new development of the chemistries in generating new therapeutic leads. So we took another anti-inflammatory disease, which is in rheumatoid arthritis. I'll not tell you the reason behind that because this audience is very much experienced to know that benefit of the COX-2 inhibition. So when we started thinking about doing molecules in the COX-2 inhibition, we did a thorough literature search to identify that what are the essential structural features a molecule should have, so that we can think about it might be a COX-2 inhibitors, and we realized that it has to be a central ring, generally heteroaromatic, and should be flanked by 2 adjacent ring, which might be a combination of aromatic and heteroaromatic. So traditional molecules, what we have, it has a heterocyclic ring at the center and a combination of 2 aryl moons. So what we did, we reorganize the structure. We consider a central ring not as a heteroaromatic, is a aromatic, and then it might be a combination of aromatic or heteroaromatic or both of them. So 3A scaffold is a completely new scaffold designed by us for the projection of the COX-2 inhibitory activity. So once we have designed, now the chemistry come into the picture, and we realize that very easily you can make it the practice, the Suzuki coupling reaction for making a biaryl, and we did it, and we prepared a appreciable number of the compounds, and maybe around 24 or 25 compounds, and with that, by subjecting them to COX-1 and COX-2, and then IC50 value, we found out these are the 3 best active compounds showing a very good selectivity towards COX-2. Then we compared these 3 compounds in the Radko edema model in 2 doses, and compared with the non-selective diclofenac and a selective acylic oxide. We found out these 3 molecules either equivalent to or even better than both the molecules. So we are very much happy that we have a very good, and Radko edema reduction is more than 65%, which is considered to be a very good. So then we want to know whether do they have a desired therapeutic potency or not. We subjected them to various kinds of hyperalgesia tests. So we took the molecule to our pharmacology collaborators, and they did a 3 pharmacological model: planar test, Fanfre test, and the silico test, silicose test. So in all the cases, this one of the compounds were parallel to salicoxibs, and other molecules are little bit inferior. Then we realized that the major problem of the set of the COX-2 inhibitor is their potential cardiotoxicity. But problem is that as of now, there is no biomarker which will be a predictive measure to tell that this molecule is going to be a potential cardiotoxic. So we have no other way but to go the classical way. So this shows that one, it doesn't have a tendency to do ulcer formation, means being a COX-2 inhibitors. So we do a little bit preliminary safety pharmacology to see that whether they might have a priori indication for the cardiac problem. We did find out that this molecule doesn't have a tendency to manipulate or alter the blood pressure. And having been satisfied all the parameters, we took these molecules to, we have a very good, at Naipur Mohali, a very good school in the formulation and pre-formulation studies. We have handed over these 3 molecules to them, and they did all the studies, and they gave a recommendation that compound 1 is a BCS2 and compound 2 and 3 are BCS class 1. So they may be either solid dosage form or injectable form. So before we took it further, we realized that ideally we would like to have a class 3. So still there is a possibility to make the molecule. Then we relooked into our chemistry. We found out whatever the changes we try to do, this is coming from the aryl part is coming from the boronic acid. We give enough variation. I probably there is not much scope to have any different boronic acid. We didn't have a much scope to change anything in the central aromatic ring and of course the oxazole ring. So we thought that before we take it further, let's see whether we got the best molecule or not, and we have to make a very quick decision. So here comes the late stage functionalization of bioactive scaffold for the lead optimization. So what we realized that this is the way we are making the molecule. It is a Suzuki coupling reaction, and generally the reaction takes place 2.5 to 6 hours. Average yield is around 65 to 70%. So each and every molecule we have to do a little bit rigorous purification, and that is time consuming. So we thought that can we have a very robust method which will be a little bit faster, if not faster, at least close to more than 80% of the yield, reaction yield. So then what we do, by this time we know the nanocatalysis has come. So we have initially tried the palladium nanocatalyst. It didn't give much improvement. We have taken nickel nanocatalyst, has been a very good replacement of the costly palladium, and nickel nanocatalyst also didn't do good. But when we have generated palladium and nickel nanoparticle together, and we found out the reaction is very much efficient and takes place with a much better yield and with a lesser activity also. So we claimed it. We have proved all those things that it is a very closely spaced palladium and nickel nanocluster, and there is a distinct evidence for that. All the analysis we have done, whatever is required to claim for a nanocluster. So with this, we had better improvement, but still we found out that anyway we have to take the corresponding starting metal for further variation, and which is going to be corresponding bromo compound, and this is the root cause of all the kinds of environmental issues. So by this time, the CBr activation has been replaced by a CO activation for making the biaryl, because of the various kinds of oxygen-containing aromatics are available. Most importantly, hydroxyl group can be manipulated to a better leaving group, and probably the reaction can be made faster. So we need a general structural feature having the benzoxazole moiety over here and adjacent position hydroxy. But these are not commercially available except if you take 2-hydroxy or salicylic as a starting material. So it is very difficult to have that. So then we realize that here is a case to put into use the aromatic stage hydroxylation. So can we convert this thing into the hydroxylation so that we do not have to start from a hydroxy related compound directly. So we went to the literature. We did find out about 3 or 4 publications are there, and again we analyzed that those are not probably the method of choice, and we had a different strategies has a distinct scope. So what we found out that we can have a direct hydroxylation by using this procedure. 2.5 mole% of palladium acetate in presence of sodium dithionate and dioxane. So dioxane is not merely a solvent here. We found a hydroxyl group is coming from the dioxane. So first we have established the reaction works very well with the versatile substrate. Those things we can use for some other purpose also. Although to start with will be only a few molecules we want to make the hydroxy compound. So this is the way the reaction goes. So this is how actually the hydroxyl radical is being generated by oxidation of the dithionite. So to prove it, we did a mass spectrometry and we did identify the corresponding A, B, C, and D. Hydroxyl radical, only we could do that thing is an EPR, but we didn't have an EPR availability. So we could not prove that hydroxyl radical, but otherwise this is the way hydroxyl radical. But by this time it is known hydroxyl radical undergoes addition to a palladium-2 to convert in a palladium-4. So in that way, mechanistic proposal is being satisfied. So having our this, then what we did method, we converted the typical substrate to the corresponding good leaving group. So these are the various ways hydroxyl group has been manipulated to a good leaving group for the CO activation. Is a methyl carbamate, ethyl carbamate, and carbonate also. So all the things which has been reported in the literature as a CO activation leaving group, we have converted it to that, and we ultimately found out a methyl carbonate or diethyl carbamate. They are the best leaving group. So here also we found out, we have tested all the various possible palladium catalysts which can be available and be reported for the CO and CBr activation. So they do moderate yield. Same thing with the nickel catalyst also. Herein also, when we get a mixture of nickel and palladium nanocatalyst, then only the reaction works very well. what additionally we found out, if the reaction is carried out while bubbling oxygen, the reaction is finished within 10 minutes reaction, and there is a reason behind that. The electron transfer becomes feasible. So we did find out a new way, a very high throughput way to make the corresponding final product through CO activation, and this is the role actually takes place. So initially in the classical Suzuki reaction coupling, palladium get inserted to the CBr bond. So here we are taking CO. It has been known theoretically also, and there are a lot of examples that when there is a competition between nickel and palladium, between a CO bond versus CBr bond, palladium prefers CBr and nickel prefers CO. So first nickel get inserted, and then palladium gets chelated with the nitrogen and transfer the electron density to the nickel, and that is perhaps the reason that with this synergistic effect makes it much effective catalyst, and the reaction takes place within 10 minutes if the reaction is, if the oxygen gas is bubbled through the reaction mixture. So we have the enough number of compounds, and those have been tested for COX-2, but we have to yet to see their other test, and then we have to make a decision whether our earlier finding molecules are the best molecule to carry further, or new molecules we have generated. So what I tried to project over you over there, that it is not like that. Organic chemistry is going to develop the reaction, and that's finished over here. And when a medicinal chemist want to utilize a particular process, he will only take 1964 chemistry. That is not the productive way to do the research. So there has to be interaction. And in this regard, what has been projected in the context of the sustainable organic chemistry, that water provides a new way to use an alternate solvent. But we did find out that what would be the advantage in taking water. In this context, we have proposed amphiphilic means electrophile nucleophile dual activation role through cooperative hydrogen bond formation reaction. In the literature, dual activation role of water, if you give a shot, the first to hit is going to come the papers published by Santosh, and another paper by Santosh's junior Sune. He is now is a drug development chemist. I think he's in Switzerland now. So, and it is a conceptual advancement in understanding the aqua chemistry. I didn't have time to tell you that one, that this early finding has been used by many other people to resolve a lot of aqueous, what is called marine natural product synthesis. And novel all water chemistries for the synthesis of the ranolazine and luminazole, and also double benefit of the nanocatalyst and water to make the versatile pharmacophore. And we did find out a few drug molecules can be very efficiently synthesizing using the double benefit of nanocatalyst and water. PD4 inhibitions, we have generated new scaffold, and initially the molecule has been synthesized by using the aqueous chemistry, and the same aqueous chemistry has extended to the synthesis of the essential starting material to generate new anti-TB leads. And in case of COX-2, we have generated through a classical Suzuki coupling reaction, 2-aryl phenyl benzoxazole is a new pharmacophore in general anti-inflammation. We are trying to project this molecule in various other therapeutic areas. The collaboration is in progress. And 3 compounds we have been found out so far, but as I mentioned, that we are trying to see whether these are the best compound or we have a little bit better compound, which we have generated through cooperative catalysis by binary nanoparticles for a high throughput Suzuki coupling reaction, and optimize the COX-2 inhibitor through CBr as well as CO bond activation, and as well as by adapting or integrating the CH activation in between, taking a ortho-aryl hydroxylation to further optimize the initially find out PD4 inhibitory lead to have a better lead. So what I try to put before you is that this I like to present it everywhere, that we know there is no doubt about that one. The modern life depends a lot with the chemical processes, petrochemicals and chemical industries, plastic, paints, everything is driven by the chemical processes. But looks like that majority of the cases, the current processes of making those chemical products are not sustainable in terms of the resources and the environmental impact. And green chemistry aims to tackle this problem, and there are real progress. But point is that green chemistry is not merely replacing all those organic solvents by water. At the heart of the green chemistry is innovation and the discoveries of new chemistry, not merely the incremental improvement of the traditional synthetic methodologies. The word green in green chemistry refers to fresh, young, and new, has been told by Paul Anastas, which is considered the father of the green chemistry. And that's exactly we tried to establish before you, that when we have used water as a reaction media, we simply have not replaced water by, we have replaced other solvent by water. We had a rationale behind that, and that rationale has been extended to get all water chemistry for all those pharma products like ranolazine and rubelazole. And each and every cases we have a distinct evidence that taking other solvent, either the reaction doesn't go, or it creates a lot of impurities, and that was the major problem of the ranolazole synthesis. I do not have a photograph of Sune and Santosh. By this time, I have taken the photographs, so they were out of my laboratory. They are well established in this thing. So Damodar, he is also has become industry's own entrepreneur. So he did later on ranolazole synthesis, rubelazole synthesis, and also was done by Dinesh. He is now in academics and Ahmedabad faculty position. I didn't talk about, but Sudipto and Kopil, they initiated the anic liquid, particularly Sudipto anic liquid work. He is now an assistant professor in Delhi IIT. And he initiated the aryl hydroxylation, and Kopil has given a shape to the nano-catalyzed work over here. Brahma is here. Where is Brahma? Brahma is there. Brahma, as I told that one in the early stage, he has taken a lot of catalyst design to make the beta blockers along with Santosh also. And we get a lot of queries from various industries regarding our catalysts. We give them the feedback. I hope they are making use of those things. So, and there are many students which I could not say. Naisargi is the person who has developed the isodos mediated chemistry over here. She is in USA. So all this has become possible because I have been fortunate enough to have a very good dedicated students. And good thing is that most of them have a pharma background. So I do not have to tell them much regarding the design. Most of the cases they used to do the exercise. And only I used to tell them that in case they are a little bit deviating from the path, I tell them this is not the path, you go other way. So it is all, they have come up with their own initiative. I have only done the supervision kind of things, right? And it has become possible because of the NICE Institute. And the motive is innovative ways to do pharmaceutical education and research. And that fruit, you can see that one, that this institute has given birth to 6 more NIPers, and extremely nice, vibrant institute. And currently, I am getting my excitement in doing whatever I want to do in this institute. It is a new IIT. Fortunately, it's a very good chemistry school. It's a new campus. It's a very vibrant campus. And till in a very short period of time, probably 12 years or so, it has made an impact, particularly the research component, though being a technical institute. And most importantly, thank you very much that under this pandemic situation, you could make time and have patience to listen to me. And I'll be very happy to interact with you.
Sir, sound is not coming, sir.
It is not coming. Let me check. Was it coming when I was talking?
Yes, sir. Yes, sir. Yours is perfect, sir. Yes, sir.
So I have stopped sharing. Let me minimize my screen, right? Yeah. So, audience cannot. The audience are muted, I guess. Professor Jindal? Yeah, I cannot hear you. I think there is an audio problem.
Sir, your voice is coming, sir. Only problem is our Anil Jindal's voice is not coming.
Yes, yes, that's what I get. I just switched off my video. The video is interfering or not.
Yeah, your voice is perfectly clear, sir. Now the floor is open for questions for audience.
It was a great presentation, sir.
Okay, Santosh, nice seeing you virtually.
Yeah, nice to see you. All those logic in organic synthesis slides and all those chemistry I learned from you, sir. Thank you very much. It was
and see that your junior has tried to continue wherever there is a scope. So whatever you have initiated now, actually Tejas, your much junior, you didn't have a chance to interact with him. He is now in LMCP college in Ahmedabad. So all his anti-TB compound based on the chemistry which you have developed only, you have taken aryl aldehyde and he has taken glyazole. So and that happens to be an essential reaction and is very, very nicely it works.
Okay, that's great to see all this chemistry, sir. Thank you very much. It's great.
Professor Chakravarti, I'm Mahesh here.
Yeah, Doctor, nice seeing you.
How are you?
You are in Dubai campus or you are in Pilani campus?
No, I am in Pilani campus only.
Acha, you are back to Pilani now. Is it because of COVID?
Nice to hear you after a long time and see you more agile and very enthusiastic about the work you've done. Is very inspiring.
Yeah. If you stay with the younger people like you, you'll remain younger.
Okay, so if there is anybody else to have a question, I thought I'll just peep in and just say hello. There may be somebody else who might want to add something. Professor Murugesan?
Yeah, yes, sir. Yes, is there any other discussion or any other interaction, please? Now the floor is open. Okay. No questions. Thank you, sir. Thanks a lot for your detailed, enlightening lectures covering all aspects with huge case studies starting from TB lead generation to PD for COPD and followed by simple NSAID analysis with excellent case studies explaining each and every aspects of our sustainable practices. So definitely, medicinal chemists, younger medicinal chemists definitely will try to implement these practices in our current work also, sir, in the future. Thanks a lot, sir. Thanks a lot for your wonderful
thank you
lecture.
in keeping me active in this pandemic situation also. So thanks for your colleagues for making the initiative, and most importantly, give me some scope to be in touch with my student, though virtually. So,
yes, sir. Always welcome, sir. Thank you, sir. Thank you. So now,
may I have your permission to leave?
Yes, sir. Thank you, sir.
I have some other meeting to go.
Yes, sir. Thank you, sir. Thanks a lot, sir.
Bye, everybody. Yeah, all the best to everybody.
Yeah, thank you, sir. Have a nice day, sir. Yes, Anil?
Murugesan, sir, can you hear me now?
Yeah. Now your voice is perfect. Yeah, please.
Okay. So thank you everyone for the participation. So this is the end of the session 2 of the International Virtual Conference on Drug Discovery and Delivery. And so we will meet, the next session is scheduled tomorrow at 9:30 in the morning. So I request all of you to join at 9:15 so that we can initiate the session on time sharp at 9:30. Thank you once again, all of you, for joining us on this conference. Thank you.
Thank you. Thanks a lot for you.